This relationship between average and instantaneous velocity that I just described can be generalized to a relationship between the average and instantaneous rate of change of any function. However, while the relationship for velocity was obviously true in any physical situation, this relationship doesn't hold true for every single function. For the mean value theorem to apply to a function, the function must satisfy two properties. It must be differentiable, and it must also be continuous. If it's not continuous and differentiable, then the mean value theorem will not apply. So this is what the mean value theorem says. It says that if a function is continuous on an interval a to b with the endpoints included because of the square brackets, and it's differentiable on interval a to b with the endpoints not included because of the round brackets, then there is some number c in the interval a to b without including the endpoints such that the derivative at c equals f of b minus f of a over b minus a. This left-hand side of the equation, f prime of c, is just the instantaneous rate of change at c. This right-hand side, f of b minus f of a over b minus a, is actually the average rate of change. This is how you calculate average rates of change. It's basically delta y over delta x. So what the mean value theorem is saying is that the instantaneous rate of change at c is the same as the average rate of change, and that there must be a number c at which this instantaneous rate of change is the same as the average rate of change. So in example 1 here, we're going to check that the function f of x equals x squared plus 2x minus 3, that it satisfies the conditions of the mean value theorem on the interval from -1 to 1. And then we're going to verify the mean value theorem, but basically going to find a c such that this equation holds true, that the equation of the mean value theorem holds true. So the first step is we want to check that it satisfies the conditions. Well, this function is continuous. Right, why is it continuous? Because it's continuous because it's defined everywhere. It's a polynomial function. There's no restrictions on the domain. It's always going to be continuous. Now, why is it differentiable? Right, it's differentiable because if we take its derivative, which is 2x plus 2, this is defined everywhere. So it's differentiable. Great. Okay, it's continuous differentiable. It satisfies the conditions of the mean value theorem. We've done the first part. Then we want to verify the mean value theorem by finding a c such that this equation holds true. So let's do the right-hand side. F of b minus f of a over b minus a is going to be f of 1 minus f of -1 over 1 minus -1. We're just going to use these two numbers, the endpoints of the interval. So f of 1 turns out to be 1 squared plus 2 times 1 minus 3, which is 0. F of -1 is -1 squared plus 2 times -1 minus 3 is -4. b minus a is 2. 4 over 2 gives you 2. Great. So basically we want to find a c such that f prime of c equals 2. We already found the derivative. The derivative is 2x plus 2. So f prime of c is 2c plus 2. 2c plus 2 equals 2. So 2c is 0. So c is 0. So at c equals 0, this equation is true. We found a c. And that c is in the interval from -1 to 1.